Hi, this is Dr. A, and this is going to be part 1 of the lecture on instrumentation in clinical chemistry. Okay, so we need to start by talking about electromagnetic radiation. So what we're most interested in is going to be visible light, but I do want you to kind of understand that all of these are electromagnetic radiation. So you have anywhere from like radio frequencies, so radio waves, to microwaves, to far infrared, near infrared. Then you have all the different wavelengths within visible light. Then you have ultraviolet, vacuum ultraviolet, X-rays, and gamma rays. The difference in these are going to be the size of the wavelength. So these are bigger, like as big as a kilometer, or in radio waves of quite a few meters, right? Big waves. And then microwaves are smaller, more than centimeters, and then way down into millimeters. And then in your visible light here, these represent nanometers. So it's 700 nanometer wavelength, 620 is orange, 580 is yellow, 530 is green, 470 is blue, and 420 is violet. You can see the numbers are getting smaller, and then here we're going even smaller and smaller and smaller. Okay, so smaller wavelength, then of course there goes from biggest to smallest in the wavelength, and then here the frequency increases, which makes sense because the smaller the wavelength, the more of them there can be in any span of time. So the frequency will increase here as the wavelengths get smaller. But just mostly remember that we have in EMR, we have visible light here, and it is divided up. The light can be divided up into different wavelengths that have different colors through all the light spectrum that go from red to violet, to all the colors of the rainbow, and each have their own wavelengths. And here for visible light, it's in nanometers. Okay, so here's a general science question for those of you who are on the Nearpod. So why do you see grass as green in color? Why do we perceive grass as green? That is obviously, if you're not colorblind, it's interesting to think about what their color might be if they're colorblind. But in general, okay, so is it because grass reflects the green wavelength and absorbs all the other wavelengths, or is it because grass absorbs the green wavelength and reflects all the other wavelengths? So pick the one that you think it is, and the answer is the color of something is determined by the section of visible light that it reflects. So for example, I have a green shirt on. It's dark green, but it is absorbing all the other light wavelengths that the light above me is emitting, and it is reflecting green, and that's why we perceive it as green. Okay. And so when you look at the color wheel, divided up like that, if you've ever seen this in art and all of that, what we have found is, again, just practical aspects of light that we've used and capitalized on for chemistry, is that if something is green, it will absorb whatever is on its opposite side on the color wheel. So it absorbs this color, so a green will absorb in this pinkish red color the most intensely. It absorbs it the most, and then it reflects the green wavelength and stuff. And so if it's yellow, is going to absorb the blue the most, and if it's red, it's going to be in this blue-green area. That's what it can absorb the easiest. Okay, so then what we can do is take advantage of that for the measurements of different solutions that are colored. And what we can do is, depending on the color of the solution, we can use the wavelength that it will absorb the most to measure the concentration. And I'm going to explain to you how all of this works. But first of all, let's just think in manners of light. So to give you an example, in a measurement of creatinine, which is one of the chemistry tests that we do to assess kidney function, the final product of the reaction is red. Okay, so it's in the red color ranges, and each analyte has its own chemical reaction that has a specific color change, and that color change then can be detected. Okay, so for creatinine, that color is red. Okay, And the absorbance for the test, if you look it up, usually it's set at about 500 nanometers, which is in the blue-green regions, which makes sense because that's the exact opposite of red, which means that that's the type of light wavelength that it would absorb the most. Okay, so the final product would reflect red. That means if you shine red wavelength on it, it just bounces off, right? It reflects it. Whereas if you shine just a blue-green wavelength into the sample, then it's going to absorb that light really well. And so how do we do that? How do we divide up the light into its components? Well, you can use a wavelength selector. We're going to talk about those here in a minute. And that wavelength selector can just only transmit that section of the visible light that you want it to, that's optimal for the absorbance of the color, that final color reaction. So every test that we do, depending on the end product of that chemical reaction, would have a different wavelength that is being measured at. And then basically how much of that blue-green light is absorbed by that solution is going to be proportional to the creatinine concentration here. And so here's an idea, an example, just to illustrate that. If, so these are different cuvettes, let's say, and these are all different measurements of creatinine. There are all different variations of the color red, but you can tell that this one's a lot more diluted, this one's a lot more concentrated. So this could correspond to a really low creatinine reading, whereas this one would be concentrated, be like a really, really high creatinine reading, and maybe something, this one would be maybe a normal one. Okay, and so the chemical reaction happens, you have the color that is formed, the intensity of the color is completely dependent on the concentration of the analyte that you're trying to detect, and so we're going to see you can measure how concentrated, in our instance here, how red the sample is to determine how what the concentration of the analyte that you're trying to detect is. Okay, so first little application here. For example, if the reaction color, the end product of your sample, is yellow, what section of visible light should you use for the detection of the absorbance? So you have your color wheel right here that you can look at, and then you have your options going to be yellow, orange, blue, blue-green, green, purple, and red. So select which one you think it is. Okay, so next we need to talk about the Beer-Lambert Law, because this has to do with the relationship between the light that can be absorbed by the sample and its concentration. So we're going to explore that so you can understand how that works. Okay, so the Beer-Lambert Law says that A, which is the absorbance, equals little a BC, okay, or epsilon BC. Little a is the absorptivity. It is the extinction coefficient epsilon. This is something that is going to be determined by the manufacturer of the reagent of that analyte, okay? And then little b is the path length of the cell, so it's going to be the cuvette, usually in centimeters. And so here's an example of a cuvette here. Turn around there. And that is obviously going to be set by the manufacturer. It can change from one analyzer to the next, the size of the cuvette or wherever the reaction is happening. So that would be also determined by the manufacturer of the analyzer or the instrument. And so these two are set, right, for each analyte. And so then we have the absorbance and the concentration. And so A, the absorbance, equals little a times B times C. We know little a, little b is set by the manufacturer. And so that can means that we can get the absorbance measurement. We're going to see how we do that. And from it, we can determine concentration. And so here in this illustration here, you see a cuvette with a chemical reaction happening. This color apparently here is blue. And then here is light that's shone into the cuvette, through the cuvette. So you're shining light through the cuvettes. And of course, the more intense that color is, the more concentrated that color is, the more of the light is going to be absorbed at whatever specific wavelength. There's going to be yellow here. Is absorbed, and if it's very concentrated, a lot of it's going to be absorbed into the sample, and very little will come out on the other end and be transmitted through that cuvette. Okay, And so this is where you can measure the transmittance. So transmittance is how much light ends up, on the other end, passing through the sample, and the absorbance is going to be how much is absorbed by the sample. And so here in this diagram, you can see kind of the relationship. So something that has a very low concentration, nearing zero, is going to have 100% transmittance. The light's going to be able to shine all the way through. It's going to be really dilute. It might even look completely clear. Okay. Something that is really, really concentrated is going to have really low transmittance, but high absorbance. So the transmittance relationship, where the transmittance here is in percentage, is like an inverse logarithmic relationship here. So the higher the transmittance, the lower the concentration. In here, the higher the concentration, the lower the transmittance. But it's not a linear relationship. Okay. But with the absorbance, that relationship is linear here. So basically what happens is the more concentrated something is, the more it absorbs. So if you plot, for example, at this concentration, so we could say that this is 1 grams per liter, then the absorbance, the plot for the absorbance, the point is probably going to be something like, let's say, like 0.3. Okay, so you got there, that's the relationship, and then it should double. So if this was 1, this would be 2, and that should be like 0.6, right? And then if this is 3, then it might be right below 1, so it might be 0.9 or something like that. And so as long as that relationship is constant, this line is going to be straight, and so it's a linear relationship. This is what you want. If it is linear and straight, then it's predictable. Now, how do you set this line? Okay, this is the line that says A equals ABC, or absorbance equals the absorptivity, the cuvette length, and then the concentration. Okay, that is determined by running known concentrations of the analyte that you have and getting their absorbance reading, and then using the known concentrations that are entered in there, and then in the plot of, let's say we said 1, and then the absorbance is 0.3, and plotting those points, and then determining the straight line that passes through it. Then once you have done that, and you've used known concentrations to get the absorbance reading at those known concentrations, and set this line, which then becomes what we call the calibration line, then if you have a sample that's an unknown for that specific analyte, you can have the chemical reaction, shine the light, get the absorbance of that sample, and use the absorbance to predict the concentration. So then we work the other way around. So let's say, the absorbance was 1, then we had said something around being around 3. It might be 3.1 or 3.2. So that's how we use that. And so for each analyte in chemistry, you're going to have a calibration curve of some sort, a calibration line usually is called, where we use standards to determine the absorbance at known concentration, and then we calculate the slope and y-intercept of this line, and then that function line is used to calculate the concentration of your unknown samples, your patient samples, as you get the absorbance reading on them, and you can get concentration. Okay, so something to specify here in the Beer-Lambert Law is there's such a thing as measurement range. So you can measure an analyte throughout the range of concentration as long as that relationship is straight, is linear, it's predictable. Okay, as soon as it starts deviating off of this linear relationship, then you can no longer predict it accurately, and so therefore you cannot measure. So like here, if you would draw the line, anything beyond this concentration is not linear. It is beyond the linearity of the analyzer, and is beyond basically its analytical measurement range. And there's a measurement range for every analyte that we do. I'll give you an example for creatine kinase, CK, an enzyme that's found in muscles, a lot of time the linearity is from 0 to 1,000 international units per liter. Normal concentration should be less than 200, so you should be able to get a reading on a normal sample or even something that's slightly elevated. The thing is that sometimes for CK is they can get really high. So enzymes can go crazy high. So if you had a patient that had a CK level in their sample somewhere around 20,000, what you would have to do is probably dilute it to a 1/20th dilution to just get it to read in this analytical measurement range where you can get a reading. So your 1/20th dilution, maybe you get a reading of 600, right? And so then its actual concentration of the sample, you could take the 600 international units reading of your 1/20th diluted sample, multiply that by 20, so 12,000 would be your result for that sample, for example. And so that's the idea of the measurement range. So you have to stay where this line is straight to be linear, to be, to be in linearity and where you can measure. And anything beyond the measurement range usually then requires a dilution to get back into the analytical measurement range. And then once you get a reading on that diluted sample, subsequently you would want to multiply that result back by the dilution factor to find the original concentration in the sample. Okay, so that's the idea of analytical measurement range. Okay, so if we plotted these concentrations as 20, 40, 60, 80, 100 grams per liter or milligrams per deciliter, whatever you want to call it. I mean, it's gram per liter on this thing here. So if you were at 40, okay, so 60 reads 1, something like that, close to this. So if you were at 40, what do you think? And so this is a draw it feature. If you're just watching the video, you can try to answer it. You just guesstimate it. And so for those of you who are doing the activity, then you can actually use this, select a color, and then just draw a number here, what you think it is. Again, it's fine to be approximate. Okay, so that's just an activity. And then this is an open-ended question again for those of you that are on the activity nearpod stuff. So this is just to jog your memory. Again, how would you establish that function line, this calibration line here highlighted in yellow? How do we do that? Okay, so put your answer in here. We just talked about how we establish that. So go back and fill that in. All right, so now we're going to talk about spectrophotometry. So the spectrophotometer is the workhorse of a lot of these big chemistry analyzers. So they are usually big chemistry analyzer or a mix of different modules and components, and the spectrophotometer is definitely an integral component of these big machines. So let's talk spectrophotometry. So spectrophotometry is dependent on the light absorbing properties of the end product of a chemical reaction. So each analyte that we can detect by spectrophotometry is going to have a specific analytical reaction, chemical reaction that is going through, and the end product is going to be a color of some sort. So a chromogen usually is required in the reaction, something that will change color proportional to the concentration of the analyte that we're measuring. Okay, so just to make it clear, photometers, right? Photo just measures light without specifying the wavelength, whereas spectrophotometers measures light at selective wavelengths, that's what we're interested in. So we select a wavelength in the spectrum of wavelengths from red all the way to violet, right? We select the specific one that we want, and we use just that specific wavelength for the measurement of that specific analyte. And different analytes are going to have different chemical reactions with different chromogens, which then, they'll each have a different color of the end reaction, which then will dictate what wavelength is going to be used to detect it. Okay, so the basic component of a spectrophotometer are going to be a radiant energy source, so something that will emit some light. wavelength selector, so something that can break that light up into the different spectrums of the wave of light, right? So red, purple, blue, whichever one you need. So something that can select that and break it where you just have that specific wavelength. So here it's orange, being so it's red, orange, yellow, green, blue, violet. Here, so we get the light shining. This is a diffraction grating, and it's breaking it up, and then it's just shining orange through. There's usually some kind of slit thing that will only allow orange to shine through. And then it needs a sample holder or a cuvette. So again, something similar to this, right? Totally determined by the manufacturer. This is where the chemical reaction is happening. That's absorbing this orange light, and how much is absorbed and then how much is transmitted is going to be detected by a photodetector. And then what the photodetector does is it translates the light that has been transmitted as absorbed, the intensity of the light that's hitting the photodetector here. So what's been shown through minus what's being absorbed is what's being transmitted is going to shine on here, and then that can be converted by the photodetector into an electrical signal, which then is connected to a readout device that will display the reading. So I'm going to play this. So I have it where you can pick up audio, but I may just talk through it. So this is it's a video of a basic spectrophotometer and how it works.
Here's how a spectrophotometer works.
Okay.
A lamp provides the source of light. The beam of light strikes the diffraction grating,
So
which works like a prism and separates the light into its component wavelengths. The grating is rotated so that only a specific wavelength of light reaches the exit slit. Then the light interacts with the sample. From this point, the detector measures the transmittance and absorbance of the sample. Transmittance refers to the amount of light that passes completely through the sample and strikes the detector.
Right, so transmittance
Absorbance is a measurement of light that is absorbed by the sample. The detector senses the light being transmitted through the sample and converts this information into a digital display.
Readout. And that's it. That's a basic spectrophotometer. Okay, so let's talk about the different radiant energy sources. So lamps have to be able to provide polychromatic light, so light that can be split into that entire spectrum, okay? And so that's not always apparent. So some light, types of light, when it splits, it's only like maybe red, blue, green, or something like that. You want the full spectrum, so you want full spectrum light. So for the visible region of the electromagnetic spectrum, so from our red to our violet, okay, usually you want to use a tungsten or tungsten halogen lamp. So these are the types of lamps. As a side note, like, don't touch these bulbs with your fingers and leave finger tip marks and stuff like that on them. You usually want to handle them with gloves, but then also with like chem wipes and stuff, and just don't usually handle it by the plastic part and not by the glass part. Okay, for UV radiation, so ultraviolet light, you want deuterium here light bulb. And if you need both UV and visible range, xenon light is usually what is used. Laser can also provide intense radiation at a narrow wavelength with minimum scatter, so laser can also be used as a light source. Then you have a wavelength selector. So that is a device that will select the light wavelength, or usually that can break the light up into specific colors. It is called a monochromator, mono for one, chromo for color. It takes all the colors of the light and just selects one of the wavelengths, one of the colors. So it selects yellow, it selects blue, it selects red, whatever, okay? And it transmits only a narrow band of the light spectrum, so only the wavelength of red, only the wavelength of yellow, okay? The types of monochromators or wavelength selectors are filters, simply colored glass. That's the first and most basic one. Prisms, so you see a prism here where when you shine light into it, it is based on refraction. It bends the light and it scatters it. This is the principle of why you see rainbows when there's sunlight and there's been rain. The drops of rain act as prism and refract light and break it up, and you can see the rainbow. Okay. And then you also have grating monochromators. They split and diffract light using holographic grating. So you can see in white is just the light that's shone, and then as it bounces off this diffraction grating, it splits, kind of like the prism does. It splits into the wavelengths, and then you can just select the specific wavelength that you want. And then another one is fiber optics. Fiber optics can be used to select wavelength to only transmit a specific, emit a specific wavelength. Then other components, of course, you have your cuvettes, right, where your chemical reaction happens and where the color change happens and stuff, and through which the light is shone and then transmitted. And then the photodetector on the other side of the cuvettes from the light that is perceiving or picking up the light that's been transmitted through the cuvettes. And it will convert that light that's transmitted into an electrical signal. You can also use a photomultiplier tube. So if the signal is the light that's being emitted is weak, or there's just not much of it just inherently, this can multiply it, and it always multiplies it right about kind of the same way, same amount, and so to make it where it can be detected. So it's a photomultiplier tube. Same principle. It just detects the light. And then, of course, you need a readout device in the computer that takes that electrical signal and converts it to an absorbance reading or something that, you can use. And, of course, in fancier, it's an absorbance in concentration. So what kind of monochromator is used in this diagram of a spectrophotometer? So can you look at it and see what type do you think that is? Only a few listed, so... All right, and then we need to talk a little bit about performance parameters for the spectrophotometer. So you do want to make sure that the wavelength is accurate, so you can calibrate. So the analyzer, depending on whatever monochromator it's using, especially if you've just changed a light bulb, because you have to change a light bulb on these spectrophotometers, any big analyzer. And then it's going to go through and you can calibrate this, and the machine can calibrate itself to make sure that it's hitting the right wavelength. So when it needs to measure at 500 nanometers, it is actually measuring at 500 nanometers. So we have to make sure that that selection is accurate. And then the linearity. So remember, again, we had talked about it. You want that relationship between the absorbance and the concentration to be linear, to be straight. As soon as it splits and starts deviating in a negative way, where now at a higher concentration you get a lower absorbance than what would have been predicted, or a positive deviation when it goes here, where you would get at a higher concentration a higher absorbance than what you would have predicted. Anyway, either way, when the relationship is no longer linear, that linearity is lost at about this value right here of concentration. And then, therefore, any analyte that falls beyond the linearity of the analyzer, usually you get some kind of signal that says too high to read, or something like that, where, or, sometimes it does little stars or something like that, where a way to indicate okay, this is beyond my linearity, I can't read it. And then that prompts you to have to dilute the sample. And with experience, you learn how much to dilute things. It really depends on the type of analyte you're measuring. The general rule of thumb is always to start with small, dilutions like a 1/2 or 1/3, and then dilute something more and more. Because the more you dilute something, the more accuracy and precision you're going to lose. And so you want to make sure that you dilute it if it needs to be diluted, but you don't dilute it too much. Okay. And sometimes that means that you may end up having to do this over and over until you hit the right dilution to get reading. You also want to make sure there is no stray light entering the spectrophotometer, since the whole measurement is based on light, any kind of light from from the room or something like that would mess with the reading. So the light that is being emitted needs to come just from the light bulb and not from the surrounding area. And so the stray light should be less than 1%, and the machine can self-check and detect that. And if there's too much stray light, like if you've changed a light bulb and you've not put the cover back on that covers where the light is, if that's not snapped on right or whatever, then there could be stray light coming in, and that could cause some problems, and it wouldn't calibrate right and stuff, and it would give you all kinds of error messages and stuff. To check absorbance accuracy, there are some NIST standards, or basically a set of glass filters to make sure that the absorbance of the sample is accurate and stuff. All right, so then we're going to move on to something that's somewhat related to spectrophotometry. It's called reflectometry. So this is a different type of instrumentation. This is reflectometry is a principle that the urinalysis dipstick machine that read the machines is based on. There are a few chemistry analyzers that are like very point of care, not high volume at all, that can do some chemical analyses like this on dipsticks, kind of like the urinalysis dipsticks. But again, they're not widely used. So the reflectometer is a photometer, so it shines light. There's no wavelength selector or anything like that. It just shines light on a sample, and so it measures the amount of light that's reflected by the sample, the liquid sample, that's dispensed on a non-polished surface. So here it would be like on the strips and stuff like that. So basically it shines a light on it to see the color, and then whatever color it is, the square's turn, it will reflect that color, and that's going to be detected by the photo detectors detecting green, and then the intensity of it also, of how much green or how much blue or how much whatever color it is detected, and then that's translated to the reading. So for the urinalysis, it might be to a specific concentration of protein or a specific gravity or pH or something like that. Okay, refractometry. So it's used in some labs. The principles of refractometry is based on the refraction of light. So that's the bending of light as it passes from one medium to the next. So for example, from air to glass, here the light bends, and then as it leaves glass it bends again, and that's if the difference between the one medium and another is different enough. So air to water, air to glass, etc. You can see the light just bends and changes. Okay, and the ability of a substance to bend light is called its refractivity. And the only really real application I can give you to this that I've personally had was a handheld refractometer, commonly used in a clinical lab. It is used to measure the specific gravity of urines if they are beyond what the urine dipstick can read. So in some labs, this may not apply obviously to every lab, but we used to do that. If the specific gravity reading was high, they wanted us to then drop the urine on the refractometer and get an actual specific gravity reading on that sample. There you go. So anyway, refractometry, bending of light. Okay, so molecular luminescence, we're going to, spectroscopy, we're going to talk about fluorometry. So fluorometry is basically fluorescence. Things that fluoresce are things that like glow in the dark. So the principle of fluorometry is it involves an exciting the fluorescent compounds with light, with EMR, electromagnetic radiation. That's usually high energy, short wavelength. So, and our fluorescent stuff, or glow in the dark stuff. If you had a glow in the dark star or something when you were little, if you shone light on it, so you turn the room light on, or shine a flashlight on it, like kind of load it with light, then when you turn the lights off and make it all dark and look at it, then it glows. And it glows because it first picked up the light from the room or the flashlight or whatever. And the glow is a lower energy, longer wavelength electromagnetic radiation. or light. So it's not shining as brightly as the room light was or the flashlight was. And so that's the principle. So what do we do with this? So there are compounds that fluoresce, and what we can do is we can attach those fluorescent molecules to antibodies, and that's or antigens, and that's its biggest application is going to be in immunoassays. You can also attach it to DNA probes or nucleotides and stuff like that. And so you can use this in, for example, in fluorescence polarization immunoassays, time result fluorescent immunoassays. So immunoassays, and immunoassays is going to have its own chapter. But in microarrays and DNA sequencing, which we're going to talk about in molecular, that would be later and stuff, not in this lesson, in a later lesson. And so if it happens in a cuvette, so it's an immunoassay, you have antigen antibody reactions and stuff like that, that's happening, and you're detecting whatever you're detecting fluoresces. So what happens is you have the lamp shines with the excitation monochromatic, shines the light, nice bright light on there, and then what is emitted, the glow, is detected at an angle. So it's not detected on the backside of the light, it's detected at an angle so that you don't pick up any of the light that's being emitted. So you bombard it with light, and then you detect the glow, and the more it glows, basically, the more of this lower energy EMR is emitted, the more of whatever compound you were trying to detect on the light you were trying to detect is present usually. But we're going to talk about in an immunoassay, it's not always like that. Sometimes it's reverse, but that's the idea. Is whatever, like using an antibody or a DNA probe or something like that, that's tagged with a fluorescent molecule, and you're looking for the fluorescence as a signal. And then luminometry is chemiluminescence. The light that is produced from a chemical or an electrochemical reaction. So it produces light without heat, and it produces light without a light source. So fluorometry, you have to shine light on it to get it to glow, to get it to fluoresce. Chemiluminescence, you have a chemical reaction that creates light, and you don't need a light source at all. You just need something to detect, a photodetector to detect the light. An example that's an everyday life example on that, there's two of them. One of them is, hopefully everybody's played with this, the glow-in-the-dark sticks or bracelets or necklaces that you can wear at night at parties or whatever. And if you get one, you know that you have to break it to activate. You have to break the glass stuff inside, so then the two chemicals mix and then glow, okay? And so they emit light for a certain amount of time. As long as the chemical reaction is happening, they'll emit light and stuff. Another application of that is in luminol, used to detect blood at crime scenes. You can see them spray the luminol, and then they use a little bit of UV to get it light to get it to react. But it's the same kind of principle. So anyway, luminometry is a chemical or an electrochemical reaction that produces light without heat, and you don't need usually another light source. So you basically have a cuvette. And there's usually, so your electrochemiluminescent compound is again tagged on a part of the assay that's being detected. If you need electrode, because it's electrochemiluminescence, that would be part of the setup. And then the light that's produced is detected with a photomultiplier tube and translated into a signal. So there you go. A lot of the troponin assays are chemiluminescent assays nowadays. So why would fluorometry be measured at an angle, but chemiluminescence is not? It's just detected. So answer me that. All right, light scatter techniques. We're going to look at nephelometry and turbidimetry. So these both involve usually antigen antibody type of reactions, but in nephelometry, you're going to measure light scattered by a particulate solution, so a solution that has particles in it. So I got a little sparkly lava lamp here to kind of illustrate the idea of, little things that are floating, and so these little compounds that are floating are going to be antigen antibody pairs, and as light is shown, they reflect the light, they scatter the light, and the light scattered can be measured. Okay, so that's going to be nephelometry. And turbidimetry is a measurement of the reduction in the light transmission caused by particle formation. So it's basically the cloudier it gets, the more turbid it is, right? Cloudier turbidity, the more concentrated, the more of these antigen antibody particles there are. Okay, so that's the difference. Both have to have a light source shown through a lens, right? To the cuvette. So for the turbidimetry, spectrophotometer, turbidimetry, it's basically you're detecting how much showing up is transmitted to the other side. So obviously really turbid, there's not going to be a lot transmitted to the other side, but very clear, there's going to be a lot transmitted to the other side. So turbidimetry reads in a straight line like that. But then nephelometry is usually going to be detected at an angle, because you're shining light and then you're seeing what's scattering. So it's a little closer to fluorometry. And then our last one for part 1 here is the atomic absorption spectrometry, also known as AAS. It is usually used for the quantitative analysis of metals, which also means that this is usually something that's in reference labs or maybe research labs, because it's actually, the AAS is complex, it is time-consuming and labor-intensive to do. So this is usually not in a fast-paced clinical lab kind of thing. It is based on the principle that of the absorption of monochromatic EMR. So again, light has been split into spectrums of one color, right? Red, blue, green, whatever. By an element in its ground state with a net zero charge. Okay, so the element, the metal, as it goes through its ground state. So usually what happens is your serum sample or plasma sample goes through a flame. The flame disassociates the metal from the proteins, because metal usually are carried by proteins. And then that metal goes back to its ground state, and as it does that, it will absorb an electromagnetic radiation pattern that's unique to that metal. The detector will pick up the unabsorbed monochromatic light. I'm going to show you an example. It'll make sense here in just a second. And then the concentration of that metal is directly proportional to the absorption of EMR, and what metal it is dictated by the pattern of the EMR absorption. So there we go. If you see, this is a continuous spectrum of light. Okay, this is the absorption spectrum of sodium. So it's absorbing light in these areas right here, which is different than that of mercury. So the pattern of what is absorbed can tell you which metal it is, right? Here's lithium, and that's exact opposite of emission. So there is also atomic emission spectrometry, right? And that one also, analysis of metals and stuff like that, you can just, instead of measuring the section of EMR that's being absorbed for that metal, you can detect the section of EMR that is being emitted. Okay, so it's kind of like it's opposite. It's like you can measure one or the other. Either way, you can detect lithium and stuff. And then, again, the intensity of that absorption or emission is proportional to the amount of, an example here, lithium or mercury or sodium, whatever, in the sample. So that's AAS, and these are what they'll look like. Opened up. Obviously, you can't run them with them open. You have to close them and stuff. Samples usually go in through there. You can only analyze like one sample at a time. Again, labor-intensive, time-consuming kind of thing. But that's what you use to detect metals, especially like trace metals and stuff like that. So this will come back in our trace metal lecture further on into our semester, into our course. Okay, and so here's a little activity. If you're in Nearpod, finish that up. And then if you have a question, you put it in there. So, okay, this was the end of part 1 of Instrumentation in Clinical Chemistry. The next lecture will be part 2. And that is all for today. Thank you.